Vazan is going to talk to us about the part of the core in the thermal evolution of super-Earth.
A bit annoying.
Yes, it works.
AV. Can you find it?
Yes.
Okay, so I would like to talk about radius-mass relation of super-Earths, and actually mainly about the part of the thermal evolution of the core on this radius-mass relation. So first, let's start. What are super-Earths? Because there are many definitions. We don't have any equivalent in our solar system. So it's maybe difficult to imagine. When I say here super-Earth, I mean everything that is larger than Earth and smaller than a giant planet. So it includes sub-Neptune, mini-Neptunes, and any other definitions. So what we know about super-Earths, the first thing we know if we look about the observed exoplanets, we know that super-Earths are common. We have many of them in our galaxy. Actually, it's the most common type of planets, exoplanets. For the planets that we do have observation of both radius and mass, we can plot such a radius-mass relation, and within the regime of this super-Earth planet, we can see that there is a great diversity in the radius for given mass and actually in the mean density. And this great diversity is usually linked, yeah? It's off. Yeah, I do hear it. Is it okay? Yeah, it's not very convenient, but yeah, okay. Yeah, so we see that we have a great diversity in this, in the mean density of those objects, and usually this diversity is linked to the composition, and mainly for the fraction of hydrogen and helium that we have in those planets. Means that if we have larger radius, it's transferred or translated to a large fraction of hydrogen and helium. However, this consideration is usually used in giant planets, but it may not be the case for super-Earths. And the reason is that in giant planet, the core, and by the way, when I say the core, I mean everything in the terrestrial part of the object, means the mantle, the crust, the core, everything together. I have planets with a core and an envelope. So in the case of giant planets, the core is a very small fraction of the total mass, and therefore it almost doesn't have any effect on the contraction of the envelope and on the observed radius of the planet. On the other hand, we have the terrestrial objects, when we don't have an envelope at all, or we have a really, really small fraction of gases. And in this case, the thermal evolution or the thermal properties of the terrestrial core almost doesn't affect its radius. But super-Earth is somewhere between, means that most of the energy, because most of the mass is in the core, so most of the energy is in the core, but what determines the observed radius is the envelope. And as a result of that, super-Earth planets are much more sensitive to core thermal evolution. So in order to model it properly, or at least better than was done before, we need to model not only the envelope of the planet, but the entire planet. So we have an evolution model for a complete core and envelope structure on one grid. It means that we actually also treat the boundary between the core and the envelope. We have realistic equation of state, and we transport the heat allow for transport of the heat by convection, radiation, and conduction in all the layers during the evolution depends on the local properties. So what we find, this is one example of a non-adiabatic core cooling, means that we don't neglect the core thermal evolution but include it in the calculation. And we see that in some cases, the core can be very hot. What I show here is the radius as a function of time in gigayears. And the color is for the temperature. And we see that there are cases, this is one example, that the core can be hot for several gigayears. And this will have an effect on the radius of the planet because the cooling is on much longer time scale. So this is a radius evolution. This is the radius as a function of time for the usual case when we don't include the core contribution to the thermal evolution of the planet. So it's actually mainly the envelope. And this was done in previous works. If we do include, like what we see in the left, we see that we have a substantial difference in radius, especially in the gigayears regime, which is the important regime for us because this is where we observe these planets. Most of them are in the age of several gigayears. These have a lot of implications because it's not only the rate, the cooling rate of the planet, but it's also, if we cool on a gigayears timescale, means that the formation energy can change the long term. And so we looked also on that. I will make it very short because the time is really short. So I'll just mention that if we start with different energy budget because of different formation scenario, and the cooling of the core is non-ideal or non-fully adiabatic, we can reach very different results in the gigayears timescale. And this can be translated on this radius-mass relation to very different mean densities. What we actually have here is the same planet, same composition and structure, but with different thermal evolution scenarios, and we can infer very different mean densities for this planet. So we made it for a series of thermal properties of the core, and we translate it to uncertainties in the radius-mass relation. And this is kind of a summary of it. We have here the radius and mass, and the background is the observed exoplanets that we have both radius and mass for. And then we started, I don't know if you see these curves, these bars. This is a bare rocky core that we start a calculation with. Means everything that below is more metal-rich than silicates. And then we add 1% of hydrogen and helium on top of this core. And then we add 10% of hydrogen and helium on top of this core. And then we also considered some average irradiation. We take here the planet to be at a distance of 0.3 AU from a solar-like star. And this is the level where most of the simulations assume the radius of the planet from. Means that if you ask for larger radius, most of the previous models will just add more hydrogen and helium to reach it. But if we do include the thermal properties of the core, like for example, the radioactive heating can contribute, if we consider radioactive heating in the core, we can contribute this fraction to the radius. If we take core thermal evolution to be much slower due to much higher viscosity, for example, or mainly conductive core instead of convective core, you can reach much more in the radius in the long term. All this is for the maximal effect on the radius between 1 and 10 gigayears. And if we start from much hotter core, due to very fast formation, for example, we can reach that radius. And we end with increasing the atmospheric opacity like some studies suggested. And what I actually want to show here, that we can explain even puffy planets, not by adding more and more hydrogen and helium, but by adjusting or changing or including in the model the thermal properties of the core, which is most of the mass of this object. So yeah, I don't know if we want time to question, so maybe I just leave it like that, and thank you for your attention.
Thank you very much, very impressive. Indeed, we have time for one question now. Yes.
No, I didn't. Not yet.
The question is about tidal heating, for those who don't hear.
I think that it may be significant. I think that all the core thermal properties can be significant because it's most of the mass. These planets that we show here, this model were for 5 Earth mass planets. 90% of it's in solid material, in a core. So I do think that sometimes even slight changes or small changes in the core properties can change the picture substantially.
Thank you very much.